So the law of sines was useful when trying to solve triangles, but we didn't deal with the case where we had side angle side, or we were given side side side. So just as a refresher, let's say for example we knew two of the sides and the angle between them. Like let's say we knew this was 10 and this was 8 and this angle was 47 degrees. We can't use law of sines because there's two variables that we're not going to know. So for example, if we're going to use the 47 degrees, sine of 47, over the side across from it, and then we have to do the sine of another angle, which we don't have any other angles, over the side across from it. So for example, we could do sine of A over 10. But we're missing two of the variables, so we can't deal with that. Also, likewise, if we were given all three sides, then we wouldn't be able to use the law of sines on that as well. So what do we do in that case? Well, let's look at any triangle, ABC, and let me draw an altitude straight down, and let's label this. Let's call, do it in green, let's call this altitude Y, and let's call this piece of side A X, which would leave the other piece to be A minus X. And then in the right triangle on the right side, we're going to have the Pythagorean theorem would be c squared is equal to y squared plus the quantity a minus x squared. Now let's take a look, let me draw an arrow. Let's take a look at the other right triangle on the left side, this one right here. And let's look at y, for example. The sine of angle C is equal to y over b. So let me write that down. The sine of angle C is equal to y over b, which if I multiply b to the other side, I get y is equal to b sine C. So I can replace that in my equation over here. I'm going to write y squared is going to become b squared times the sine squared of C, angle C. Okay, plus a minus, now let's do the same thing for x in that triangle on the left. If I did the cosine of angle C, that would equal x over b, the adjacent over the hypotenuse. So let me write that out. The cosine of angle C is equal to x over b. And so once again, if I multiply that b to the other side, I get x is equal to b cosine C. So let me replace the x over here in my Pythagorean equation. And x is going to become b cosine, b times the cosine of angle C. And then that quantity is squared. Okay, so let's square that quantity. So we're going to have c squared equals b squared times the sine squared of angle C plus, now if you need to write out a minus b cosine C times a minus b cosine C and distribute or FOIL, go ahead and do that. You're going to wind up getting a squared minus 2 times a times b times the cosine of angle C plus b squared times the cosine squared of angle C. Now let's regroup this. Where are we going with this? Well, I could factor a b squared out of the first and last term, and I'd have a sine squared of angle C plus cosine squared of angle C. Uh-oh, some bells are going off. That should look familiar. Plus a squared minus 2 times a times b times the cosine of angle C. But sine squared plus cosine squared is just equal to 1. And so my final equation here is going to be c squared. I'll just switch the order. I'll write it as a squared plus b squared. You could do b squared plus a squared. And then minus 2 times a times b, let me put a multiplication in there, times the cosine of angle C. And this is what's known as the law of cosines. Notice in this equation, we're using all three sides, side C, side A, side B, A and B again, and then we're using angle C. So we're using all three sides and one of the angles. So when is this going to be useful? Well, if you go back to the example I had earlier, where I had given you side B, side A, and angle C, we could plug in all that stuff. We have A, we had B, we had angle C. We could evaluate all that and then take the square root, and we would figure out what side C is. But likewise, if we had all three sides and we were only missing the angles, we could plug in values for A and B and C, and then we could solve for angle C in this case. Now, we could do this with any of the sides and angle combinations. So let me go back one more time. And let me just point out one thing. In this equation, the only angle that we're using is across from this side, the side that's by itself in the equation. So if C is by itself, C squared, then it's going to be the cosine of angle C. On the other hand, if this was A squared by itself, and we would just redraw this and label it, the same way. If it was A squared, where's A squared by itself, then on the other side of the equation, it would be cosine of angle A. And then finally, if this was a B squared by itself, over here would be cosine of angle B. So this side here has to match with this angle here. So there's actually three different equations we could write out. So we could have A squared equals B squared plus C squared minus 2 times B times C times the cosine of angle A. Or we could have B squared equals A squared plus C squared minus 2 times A times C times the cosine of angle B. Or finally, the one that we just proved, C squared is A squared plus B squared minus 2 times A times B times the cosine of angle C. And so there you have your law of cosines, which will help you solve triangles. So between the law of sines and the law of cosines, now you should be able to solve any triangle. Let me go down and point out one more thing. If I had, for example, let's say this was 32 degrees here, and this was 5, and this was 7, and we wanted to find that side there. We can call them whatever we want. We could label it as A and B and C and angle ABC. But just understanding the relationship, I'll grab my arrow, making sure that the side that's by itself and then the angle across from that side goes here, that's what we're going to use in this case. So I'm going to have the x squared by itself. So I would just write x squared equal, and the order doesn't matter here, 5 squared plus 7 squared minus 2 times 5 times 7 times the cosine of the angle across from x, which was 32 degrees. And then we'd grab the calculator and punch that in, and yada yada, we'd get x. All right, so let's actually look at an example and solve a triangle. This might be a good time to hit pause and see what you can come up with first by yourself, and then come back and check your answer. All right, so we have things labeled here. So with angle A, that would make this side A, and angle B, this would make side B, and this would be side C. So notice we have all three sides, we don't have any of the angles. So you can start with whatever one you want. Let's say I wanted to first find out angle C. That means that I'm going to have side C by itself. So C squared, and actually I'm just going to plug in the numbers, I won't write out the formula. So C squared, which is 14, equals A squared plus B squared, so 19 squared, plus 8 squared, minus 2 times 19 times 8, times the cosine of angle C, which I don't know. So there can only be one unknown in this equation, otherwise it's not going to be of any use. So instead of grabbing the calculator as you work through this and putting in approximations for decimals, etc., let's go ahead and just solve this equation for cosine of C without even grabbing the calculator. So the first thing I would do is subtract the 19 squared and the 8 squared. I'm not even going to evaluate what those are. We know that 8 squared is 64, but that's not a big deal. Equals negative 2 times 19 times 8 times cosine of angle C. Then I'm going to have to divide both sides by negative 2 times 19 times 8. So I have cosine of C is equal to that. And then I'm going to have to take the inverse cosine of that entire fraction, quotient. So 14 squared minus 19 squared minus 8 squared. We have to be careful when I'm punching this in on the calculator. And that will equal angle C. So finally, now is when I'll grab the calculator and I'll punch that in. So I'm in degree mode. So second cosine, inverse cosine. Now I'm going to put parentheses for the entire numerator. So 14 squared minus 19 squared minus 8 squared. Close off the numerator, divided by, and now another set of parentheses for the denominator, negative 2, make sure you're hitting the negative, not minus, times 19 times 8. Close off the denominator, close out the inverse cosine function, and there's your angle C. 41, let's go 2 decimals, 41.12 degrees. So angle C is equal to 41.12 degrees. So remember, we're solving the triangle. That means we're finding all the measures of all the sides, which we already have, and the measures of all the angles. So now I have to go ahead and do it for angle A. So I'm going to erase those. We need to look at those. If you need to keep them in, keep them in. So now for angle A, I'm going to have 19 squared is equal to 8 squared plus 14 squared minus 2 times 8 times 14 times the cosine of angle A. And when I solve that for A, follow the same steps as before, it's going to be the inverse cosine of the fraction 19 squared minus 8 squared minus 14 squared divided by negative 2 times 8 times 14. And I can grab the calculator, punch that in, second cosine, another parenthesis, 19 squared minus 8 squared minus 14 squared, close off, divided by negative 2 times 8 times 14, close, close, enter. So angle A is 116.8 degrees, 116.8. Now, to find angle B, I could go through that whole process again, or since I already have 2 of the angles, and all the angles in the triangle add up to 180, let's just subtract that. 180, now notice, 180 minus, I'm going to call up the last answer by pressing second and the negative button. And then minus, and then I could also have done it this way, highlight that 41.12, enter, and then enter. So I have not done any rounding in my calculations for any of my final 3 angles. So 22.075, we're going to go nearest hundredth, so 22.08. And I have solved this triangle. So you're solving triangles when you either have side, 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 or side, angle, side. You're going to use the law of cosines. And in the other examples, you use law of sines. And make sure you're careful of the ambiguous case when you have side, side, angle, and you're using the law of sines.